Okay, hello everybody. I'm very happy to be with you this morning for you and this evening for me in California. I'm going to tell you today about the story about gravitational waves, how to detect them and what they are. Actually, that story is almost completely encapsulated in the picture that I have on the slide. That picture is the first figure from our announcement, from our paper giving the announcement that we saw gravitational waves. I'll describe it as I go along, but let me say a couple characteristics now. You see wiggly lines on the top. Those are the signals from our detectors of gravitational waves. Two different detectors separated by 3,000 kilometers. The line below that, with a little bit smoother, but almost the same shape, is the prediction of gravitational waves by Albert Einstein. And you can see the wonderful similarity between the two. Below that is how much noise there is. And below that is a picture of what we call a time frequency curve, which is a characteristic of this kind of signal. So I'm going to start at the beginning and tell you some things about gravity and then about gravitational waves. Gravity was first really understood by this man on the slide here, Sir Isaac Newton. And Sir Isaac Newton wrote a book in 1687 called the Principia. And in that book, he described gravity. He described it in a formula, which is shown here. And that is the force of gravity is proportional to the product of the masses of the two things being attracted to each other, and inversely proportional to the square of how far apart they are, times a constant that's the strength of gravity. He didn't know the strength, so he just called it G. This formula managed to describe essentially everything about gravity for more than 200 years. He called it universal gravity exactly for that reason. It described how the apple is attracted to the earth when it falls out of the tree. He described how the moon goes around the earth or the earth around the sun. It described the waves from the ocean or anywhere that gravity actually is playing. So this is the most successful theory of physics ever. He wrote it in a famous book called the Principia. There's still about 100 copies of this book in the world. And in that book, he also wrote down the scientific method. Scientific method is what was used for years for us to understand what is the truth in scientific measurements or in theories or in anything that we do scientifically. And that principle is still used today, somewhat in a little different way because we use techniques like statistics to give us confidence in what we measure. The constant in this formula, the big G that's in this formula, took 100 years before anybody could figure out how to tell it what it was. And that was done by a scientist named Henry Cavendish. He was a very lone person. He had no funding except that he had private funds. He was a wealthy man. And he decided he wanted to measure how much the earth weighs. In the process of measuring how much the earth weighs, he determined the constant that Newton talked about by the technique that I show on the right. And that is he used something which we call a torsion balance. You notice a bar coming down from the top, and then a bar across and two lead spheres on the end. The rest of it is a technique that we use now using a laser to see how it moves. He then twisted the arms just a little bit and measured how they would try to restore. And by that, he did what we do in experimental science. He calibrated the device. And then he brought up two very heavy lead weights and watch how much it bent. From that, he determined capital G. I write down below this constant as it's known today to 7 decimal points, 7 figures. And he, in this very first measurement, 100 years after no one knew how to do it, measured it to within 1% of the value that we use today. So this theory, which I'm not going to talk about, is the wonderful theory of Newton and the most successful theory of all time, I think, for physics. Existed up until the time of Einstein as our primary theory of gravity. It still is a primary theory of gravity, except in the regions where we need Einstein's formulation to give us the answers. That is places like when objects are traveling very, very, very fast, or distances are very long. So the only problem that existed at the time Einstein was doing science, which was the early 1900s, more than 200 years after Newton, there was only one problem that was not described correctly by Newton's theory, and that was the orbit of Mercury around the sun. I show it here in the slide. Mercury has a very elliptical orbit around the sun, and each time it comes around the sun, it's pulled by the positions of all the planets and the moons as it goes around, and it doesn't come back to quite the same place. How much it moves can be calculated. And when it's calculated using Newton's theory, it became 532 arc seconds per century is how far this moves forward each time around this very elliptical orbit. The observed amount was 10% larger than that, about 575 arc seconds per century. And that was the only discrepancy that existed. In fact, at that time, that discrepancy was popularly thought to be due to an object that had not yet been discovered, maybe a planet, between Mercury and the sun. We know now that there is no planet between Mercury and the sun. First, because of Einstein's theory, which I'll describe. And second, because of very elaborate missions of NASA that have looked for objects between Mercury and the sun and found nothing larger than 10 kilometers in size. So Einstein then developed his theory of gravity, in which he presented in 1915. Before that, Einstein in 1905 solved 4 of the most important problems in physics, including the theory of special relativity, which is the theory of what happens when objects go very fast and also objects relative to each other. What that theory didn't have is accelerations. And he has spent the next 10 years adding acceleration to the theory that he had developed in 1905. And that became the theory of general relativity, commonly Einstein's theory of gravity. I write down the formula for that here as well, but I'm not going to describe it in this lecture. I just do it to compare with Newton's formula. So this is a first change in gravity in 250 years. I emphasize that that doesn't mean that Newton's theory was wrong. It means that Newton's theory was not complete in its ability to understand all of nature. And that is how physics develops. We often have our best understanding at a particular time, and then we make new discoveries that modify it or add to it. In this case, a different formulation of gravity that agrees with Newton's theory for most of what we would encounter, but not always, as I'll describe. So gravity in this case isn't a force. We think of gravity as a force. What was written down as a force by Newton, but instead it's the product of space and time itself. It's built in to the actual structure of space and time. It makes it very complicated, and it's a very complicated theory. Space and time is not linear, it's curved. You hear the words like curvature of space-time, warpage of space. All that is really a description in words of what Einstein's theory does. Nothing can avoid the feeling of a curved structure. And that's what makes gravity universal in the terms of Einstein. So Einstein did this. It agrees with Newton's theory in the inverse square law and so forth for two objects, but it describes much more. It describes first correctly the orbit of Mercury around the sun. So it gets an answer of 575 arc seconds per century. And in fact, when Einstein first presented in 1914 and 1915 the theory of general relativity, the first thing he did was show that he got the right answer for the orbit of Mercury around the sun. So that was a success in the sense of fixing something that didn't come out right in the old theory. We don't usually accept a new theory in physics just because it solved a problem that existed. It usually has to have some features that it'll describe something new. And in this case, it describes some new things. But before I come to that, let me point out that it also solved some conceptual problems that existed in Newton's theory. The first one Newton realized and wrote about in the Principia very briefly. And that is, he realized that when the apple falls and you view it, that you know the apple falls immediately at the same instant that it fell in his theory. There's nothing that takes any time for the message to get from the apple to you in Newton's theory. Einstein recognized that that's really not correct. And in fact, you can visualize it by imagining right now that the sun disappeared. We would not know that for 8 minutes. And that's because it takes time at the speed of light for the signal to tell us that the Earth has disappeared. It takes that long for that information to get to us. In Einstein's theory, the information is carried at the same speed as the speed of light. And I'll point out that we now know that that's true to 1 part in 10 to the 15, a very small difference just from a measurement that we did. A second conceptual problem that Newton explained, that Einstein explained, that Newton didn't, is why the two objects, when you have two objects attract each other, why do they attract? Why don't they repel each other? And what makes them attract each other? Newton did not explain that. In fact, in the 200 years between Newton and Einstein, people tried to explain it, but never in the right way, usually using some argument of electricity. But Einstein's theory explains it. If you look at the figure here, this is a plane grid or some form like a trampoline that is normally flat. But if you put on it a massive object, in this case, I show the Earth, it distorts the space and time. At each intersection in this picture, the space and time are both distorted as you get closer and closer to the mass. You can imagine that if nothing is on this surface and I put another object on, the moon, it wouldn't do anything. But with this distortion, it will try to roll toward the Earth because it's moving at some velocity instead of rolling toward the Earth. It has a force, that's a centripetal force that keeps it at some distance. And so it goes around and around the Earth. Now, in order to do something beyond explain some conceptual problems in Newton's theory and the difficulty with Mercury, the theory, if it's a good one, should describe something new. And in this case, Einstein's theory did. rather dramatically. And that is, if I look at the picture on the left, the picture of the sun and the earth distorting the space shown graphically below it, you can imagine then that light, not just massive objects, but that light will follow this curvature. That's the curvature in space and time itself. A natural result of that is that light, as it comes near the sun, will actually get bent because it goes through curved space-time. Einstein recognized that and recognized how much it would get bent and proposed that it be tested by looking, as I show on the right, at an eclipse of the sun, and at the same time watch stars that are behind the sun, watch the starlight from that bend as it goes around the sun itself. He proposed that experiment in 1915, and it was carried out by Sir Arthur Eddington in 1919, watching what's called the hiatus star cluster go behind the sun during an eclipse, full eclipse of the sun. And this was measured in the Southern Hemisphere. This made all the headlines in the world. This is, you can read, is kind of humorously written in the New York Times. Lights all askew in the heavens. Stars aren't where they seem to be, and so forth. The journalist clearly thought this was a little crazy, but it made the New York Times, and it is what made Einstein a famous man for the public. Scientists like myself recognized that he was famous and important by the work he had done in 1905, but that didn't make him famous worldwide. It was the work, it was the bending of light that made all the newspapers in the world, that made him famous from that time on. That technique now, and this is often a lesson in science, that you learn something new, and then that becomes a tool to learn something yet newer. And in this case, the fact that light bends when it goes around an object is used very commonly now in astronomy, called gravitational lensing. That is to study an object like shown in this picture. If there's a source behind it, you can study it by the kind of bending of the light that goes around it. Or if you know that object, you can study the light that comes from an object behind it and know what made up that light. So that's very commonly done. Here's a picture, that's a common picture of light coming around a dark object. And the most famous picture of the bending of light is named after Einstein, and it's called the Einstein cross. And I show you a picture of it here. It can be observed from the Southern Hemisphere, maybe Southern India, I don't know. And it can almost be observed with the naked eye. It's very bright. All of this may seem very abstract. So to bring it a little bit closer to home before I talk about gravitational waves, let me point out that even though Einstein's theory seems so abstract, and Newton's theory is something we can kind of grab and hold on to, Einstein's theory of gravity itself is essential in enabling something we all use all the time, and that is GPS that's on your phone or to move around in your automobile. GPS requires a correction due to general relativity in order to get the right positions of where you are and where you're heading. It's a good lesson in relativity. Satellites, 24 satellites that are high above the ground, and they're traveling at 14,000 kilometers per hour. And we have a saying in special relativity, that is E equals mc squared, or the theory that Einstein introduced in 1905. We have a theory that moving clocks tick more slowly. And so there's a correction of -7 microseconds per day that has to be made for special relativity. Likewise, for general relativity, we also have to make a correction. And that correction is due to the fact that the satellites feel less gravity than here on Earth, about a quarter as much gravity. Because of that, there's a correction for general relativity. It's the opposite direction, and it's actually 45 microseconds per day. Those all just seem like numbers, but if I put those numbers together, I have to make a correction in the GPS device of 38 microseconds per day to get the right answer. If I didn't do that, then I wouldn't be able to stay on the road. If you ask yourself how long you could stay on a road that's about 10 meters wide, if you did not make that correction, it would only be 2 minutes. So the correction due to general relativity is used by us every day. And so that theory is important, well beyond being important for just the kind of limited science that I talked about. Now, Einstein made one more prediction. The next year, after introducing general relativity in 1916, he wrote a little paper, and in that paper, he didn't derive anything. He predicted that there must be gravitational waves. His reasoning was that if he looked at the equations of general relativity and he looked at the equations of electromagnetism, there were similarities in the equations, different letters and so forth, but similarities that made him, being Einstein, make the leap that if the equations looked a certain way and electromagnetism has waves, then gravity must also have waves. The paper otherwise isn't very good. It has a mathematical mistake in it of a factor of 2 that would have been terrible for us in misunderstanding what we discovered when we discovered it. He fixed that in a second paper in 1918. And in that paper, he also described what a source of gravitational waves would be. Electromagnetic waves, you might know, were discovered by Hertz in the 1880s by taking 2 charges, oscillating them with respect to how far apart they are. That's a dipole form. And noticing or measuring that in the next room, that made electromagnetic waves. He moved it forward and backward toward the source and showed that it had the wave-like structure. So Einstein then believed that must also be true for gravitational waves. In the 1918 paper, he showed that it wouldn't be 2 charges moving or 2 masses moving toward each other in a dipole, but rather it took what we call a quadrupole form, so a specific mathematical form. That form can be duplicated by a barbell going around itself, or 2 objects like this circulating around each other. The moon around the earth around the sun, or 2 equal objects or near equal objects is shown here. In this graph, you see these waves going out, and that's just in the cartoon characterizing the fact that as these 2 objects go around each other, they radiate gravitational radiation, lose energy, and spiral into each other. So gravity itself needs to obey the principles of relativity. That is, no signals travel faster than the speed of light. And I'll show you that they essentially travel at the speed of light. And gravity comes from rapidly accelerating masses. The effects at large distances can't change instantaneously, so they have to come as a signal. Gravitational energy ripples out from the accelerating object, but those ripples are not carrying anything like the photon is for electromagnetism. In Einstein's theory, it's ripples in the structure of space and time itself. So this is just a picture of what might happen. Two objects going around each other at a radius r, and you make a gravitational radiation by some rapid just change in the distribution of matter. Clearly, as I rotate, I'm changing where the matter is in space. Binary stars, that is two stars going around each other, are a perfect example of this. The more massive the stars and the faster they're going, the better. And they'll go faster and accelerate to make gravitational radiation. So the binaries could be made from, say, neutron stars, or from black holes, or gravitational wave signal that we see in this way cannot be seen in an ordinary telescope. The only formula I'll write down today is here, just in case somebody knows a little bit about general relativity in the audience. I say what I do on the left, but I'm not going to refer to it. But this equation, which is an equation that comes from general relativity, has one little funny thing in it, this h sub mu nu, and that is characteristically what we call the strain or the strength of the gravitational wave signal itself. But the form of this, for people who have seen it, looks very much the form of electricity and magnetism. So in my own way, I've duplicated what Einstein recognized in this 1916 paper. That is, if you formulate this new theory in a particular way, it has similarities to the structure of the equations that exist in electricity and magnetism, with a different letter because it's this little h mu nu. But we know in electricity and magnetism that if we have this formula, it creates electromagnetic waves. The electromagnetic waves have two parts, E and B, electric and magnetic parts, and they're 90 degrees from each other. In this case, we also have gravitational waves. They'll travel at the same little c, which is the velocity of light in Einstein's theory. And there'll be two components, just like for electromagnetism. But the two components are not at 90 degrees from each other, but at 45 degrees from each other. This is a subtlety, but it's basically to tell you that it's how it's different. And it's a factor, in fact, a result of the fact that gravity has a spin that's different from the photon for electromagnetism. It's what we call spin 2. So that's as much as I'll do on the theory. And I'll talk mostly about experiment from now on. So just the purpose of summation, if I have two objects going around each other, it's a natural consequence of special relativity and finite energy, finite information transfer. The gravitational waves will radiate and they'll propagate away at the speed of light. That is what we try to see later. Imagine then that we had these binary system and they're circulating each other. In a little freehand drawing, I show it on the left. Two objects of equal or not equal mass, equivalent to the Earth and the Sun, or in our case, it's going to be black holes, are going around each other. They may be spinning. I show that here. And as they go around each other, they radiate away energy and slowly work their way closer and closer to each other and go faster and faster. That is, they go make the circle around each other faster and faster. Eventually, they reach the second central part that I have. And that's the most difficult part for general relativity and for understanding black holes or whatever is merging, when they merge together into a single object. And at the end, it all has to settle down in a way that conserves all the things that we know are going to be conserved. And that is to give some what we call ring down, which is the part at the very end. The middle part is probably the most interesting eventually, because it tests the part of Einstein's theory, what we call the strong field limit, where maybe alternate theories will be better than Einstein's. And so we test that. On the left, we see the characteristic signal of merging objects. So what we have then is a gravitational wave passing through space. Now imagine it comes to the Earth. When it comes to the Earth, the ripples in space and time change the space itself, stretch and squash it in a way that I'll illustrate on the right. Imagine that I have a little circle of radius L and some free masses around the circumference of the circle. And the gravitational wave goes through. What it's going to do is distort that circle with the frequency of the gravitational wave, first making it elliptical vertically, and then changing to making it elliptical horizontally. And that's shown in this picture here, where the amount is incredibly small. And that's why it was so hard to detect gravitational waves, and why we live as peacefully as we do in the universe, which has basically space that's very, very stiff. And so most things don't do very much to it. And we believe everything is more or less in straight lines. It's not quite by Einstein's theory. So the amount of this little distortion, or making the circle more elliptical, is about 1 part in 10 to the 21 for the objects that we measured, black holes. If we had then a circle that was 1 meter in size, the size that we'd have to measure, the distortion that we'd have to measure is 1 part in 10 to the 21, an incredibly small number. In fact, I show here what we do. We try to do this by the most sensitive technique that we know how to do measurements as men, and that's what we call an interferometer. We shine a laser beam in from the left, reflect half of the light up on the screen, half of it straight on through. And if there is no gravitational waves and the two lengths are the same, then the light will go down both arms, come back at exactly the same time. If we invert one compared to the other, they'll cancel. So we basically see no signal. But if, as shown in this picture, it distorts at some frequency, I have a frequency here of a couple times a second, then you'll see the light, the difference in length will change the phase of when they come back, and you'll see a signal. All this looks very good in this little picture, but because the effect is 10 to the minus 21 is such a small number that even in the apparatus that we made, where we make the apparatus not a meter size, but a kilometer in size, so that the effect is 10 to the minus 18 meters, it requires us to make an instrument that can measure a difference in the comparison of the two sides to 1 part in 10 to the 12th of the wavelength of the light. And the second challenge is that we have to somehow eliminate the shaking of the Earth to also 1 part in 10 to the 12th. Those were the two challenges that took us a long time to become 20 years to become sensitive enough to detect signals. This is a picture of our detectors. They're identical, but they're not in identical physical locations, but they're identical instruments and they perform identically. They're 4 kilometers long on a side, and they do what I just showed in that picture. A light from a laser is sent down both arms, split, sent down both arms, and we compare how long it takes to go down one arm compared to the other arm. And if there's no gravitational wave, they come back at exactly the same time. If there is, then they come back at a slightly different time, and that's what we measure. These two instruments are 3,000 kilometers from each other. Now, I said we have to measure 1 part in 10 to the 18, or 10 to the minus 18 meters. Let me remind you what that is. 1 meter, we all know. A human hair is about 100 microns, or 1/10,000th of that. The wavelength of light, like we're using to show on this screen, is about a micron, and that's 100 times smaller yet than the meter. An atom, an atomic size, is 10 to the minus 10 meters, or 10,000 times smaller than the wavelength of the light that we're using to draw this picture. And a proton diameter is 10 to the minus 15 meters, or 100,000 times smaller than the atomic diameter. And LIGO sensitivity is 10 to the minus 18 meters. So we're measuring much, much smaller than the size of a proton. I'm showing once more what the interferometer looks like. So the interferometer basically has light going both ways, and there's no difference when it comes back. They cancel each other if the lengths are exactly the same. I show it here with waves, which is what light is. When it comes back on this axis and comes back on the other, if they're exactly the same, they just cancel. And my detector, which is off on the right, sees nothing. But if they slightly change in length, like I show now, then they line up and we get light and we detect a signal. And so schematically, that's what the interferometer does. You can see it light up and go dark. This is a picture of the apparatus itself, so you can see it, LIGO. Big tanks. I don't show a man on this, but a man goes about a third of the way up these tanks. All those ports are to put mirrors and lasers and electronics in the interferometer itself. The long arms go off to both sides of the screen in perpendicular directions. There are a lot of interferometric tricks that we had to learn to make an interferometer work to 1 part in 10 to the 12th, as I described, which is orders of magnitude better than ever done before. But I don't have time to describe that. I'll describe the other just briefly. In order to get rid of the shaking of the Earth, believe it or not, the shaking of the Earth seems stable to us, but it shakes far too much for these measurements. We do 2 things. First, we use shock absorbers, much like in your car. A shock absorber in your car, when you go over a bump, it goes up and down, but you don't feel it very much because that energy is absorbed and moved to lower frequency by shock absorbers. And so we have 4 layers of the fanciest and best shock absorbers we could possibly make. But that got us to maybe 10 to the 10th rejection of the ground. To get the rest of the rejection, we use seismometers that measure the residual shaking of the Earth and active probes that push back against the shaking of the Earth. And that got us to the 10 to the 12. Also, the interferometer itself, the mirrors, as indicated in the picture on the left, hang like from a pendulum rather than be steady on a table. And this all isolates the mass so that it's free to move without signal. Once we achieve that, we saw the signal that I showed on the introductory slide. I'll notice now that the scale on the left says 10 to the minus 21. That's the scale that I talked about. So this was the scale we're able to measure smaller than that. The biggest part of the signals are 10 to the minus 21, but they're smaller than that over on the left. The top pane is the data from one of our interferometers in Hanford, Washington, the middle one in Livingston, Louisiana. And the bottom is just a superposition, one plotted on top of the other, slid just slightly, 6.7 milliseconds to be in line with each other. The second one, those are shown again on the top of this graph, and with Hanford, Washington on the left, Livingston, Louisiana on the right. The second pane is Einstein's calculations. And as I said, when I started, the third one is just the difference of the two, which is the residual noise in the instrument itself. Coming out with that is what established the discovery. And my colleagues and I, shown in the middle, won the Nobel Prize, and this is the ceremony. Since that time, we've made another pretty spectacular discovery, and that was the discovery of the merger of two neutron stars. Black holes have a name black holes because they can't be seen by anything. They don't let any light out. All light is bent to be kept inside the black hole. That's the definition of a black hole. So they couldn't be seen by telescopes. But when we see a merger of two objects, but they're neutron stars, neutron star is the product of the collapse of a star after it burns up all its fuel. And the merger itself can give gravitational waves, and after they come together, it can give nuclear signals, including photons, which were observed in a detector here. So the picture on the left shows our gravitational wave signal, shown in the very bottom pane, and the line that comes up. And 1.7 seconds later, you see the peak. Those are high energy gamma rays detected in a satellite. And that object, once we figured out what it was and where it was 150 million light years away. That means it was 1.5 10 to the 15 seconds away. So within 1 part in 10 to the 15, the fact that these signals come at the same time means that light and gravitational waves travel at the same speed, to 1 part in 10 to the 15. We then looked at where they came from. And you can see the picture on the right shows a shaded region, which is Fermi. That's how well located the gamma rays were. And inside of that is our picture of where they were located. This enabled us to alert the whole astronomical community to look for this, from gamma rays to X-rays to radio. And with that, we got signals from all of those that were detected. And from that, the data fit a model for how a neutron star merged to a binary neutron star merges that has probably helped us answer a question which we couldn't answer before. Nothing to do with astronomy really itself, but it's always been a puzzle how, when the Earth was formed, heavy elements got into the Earth. We know that in the universe, it's mostly made out of hydrogen and helium. Beyond that, we know that in stars that burn, they burn by the fusion process. And that starts by burning light elements like helium, then lithium, then oxygen. But once it gets up to iron, it can't work anymore. So how do you make elements that are heavier than iron? It's been a puzzle, which we really didn't have a good explanation for since I was a student. Now it turns out that the merging of two neutron stars is a very good source for making these heavy elements. For example, you can ask, how did the heavy elements that are in the table get made, or how do we know they're there? Not naturally in nature, but how do we make them in the lab that they have names and so forth, the heavier ones than iron? They're made generally by taking a neutron source and bombarding it into a heavy element and then making yet heavier ones. So that's very much like the collision of neutron stars. And in fact, if you take then the best calculations we can do of how many neutrons were made in the collision that we observed, it made a lot of gold. Neutron star merger is very, very efficient at making gold. In fact, the collision that we observed by calculation made 100 Earth masses of gold. That's a lot of gold. That, of course, didn't get the gold in the Earth, but there presumably were neutron star collisions in ancient times before the Earth was formed that made heavy elements that got into the Earth. So that now represents our best picture of how heavy elements got into the Earth. We're not done. Let me just end by showing you that we now know exactly what to do to make better instruments. Just like in telescopes, we made better and better telescopes. We can make a bigger device. We can make it quieter by cooling it down. We can have special optics to make it better and better. So over the next decade or 2 decades, we will see a steady improvement in these detectors and more discoveries using gravitational waves. Someday, maybe we'll be able to study gravitational waves even from the early universe. We all know that the early universe is a big puzzle. What was the Big Bang? Even after that, what was this thing called inflation? And presently, the only way we have to look at the early universe is with photons, but they only go back a few 100,000 years after the Big Bang, because the universe was opaque before that, and you couldn't see back further. In principle, you go back yet further with neutrinos, but they're so low energy that they're very difficult or maybe impossible to measure, but they can go back in principle to the first few seconds. So that may be possible someday, but it looks unlikely. And probably the best way in the future is probably 100 years away, because we don't know how to do it, to study the early universe at the very earliest times is with gravitational waves. So we're in a situation now which isn't so different from a few years after Galileo. Galileo in 1608 took lenses that were originally made they were at that time able to make good lenses for glasses, and made a telescope and pointed at Jupiter. He noticed that there were 4 shiny objects in Jupiter that couldn't be seen with the naked eye. He thought at first those were stars, but then as he monitored it for a few days, they didn't move like stars, but rather were moving close to the planet itself. And so he discovered that they were actually moons of Jupiter. That was the first case of modern astronomy, that is, understanding the sky and the universe beyond what we can do with our naked eye. We've now had 400 years of astronomy, and what we've learned about the universe is phenomenal. We're now, in a similar way, at the very first stages of being able to look at the universe in a very different way. And that is looking at the effects of gravity instead of effects of electromagnetic radiation. And I believe, given 400 years, we'll learn a lot from gravitational wave astronomy. Thank you.